In the beginning, ends of time and darkness. Nothing. In the vast reaches of space, a few lights appeared. Great clouds of dust and gases moved silently in cold darkness. In that incredible void, materials formed. Masses appeared. One was a sun. A nuclear furnace was born. As the sun grew in size, its gravitational pull increased. And it captured other planetary masses to orbit around itself. For 500 million years or more, the Earth, third planet from the sun, was a cold and lifeless body. Slowly, inside the whirling sphere, internal temperatures began to rise. Heavy metals condensed, melted, and sank into the global center, forming the red-hot molten core that exists today. Enormous interior heat carried materials upward, pushing them to the surface. Melted rocks, lava, cooled and formed a crust. Then eruptions and earthquakes cracked the crust, forcing it up and down. The crust buckled and pushed against itself, forming mountains and plains on the cooling surface. Gases and water vapor, trapped in the rocks and fire, released by the intense heat, rose into the air, forming clouds, which condensed and fell back to Earth, creating rains which fell incessantly, eroding the rocks and filling the Earth. Rains pounding down on the smoking Earth. For millions of years, the rains fell. More atmosphere was formed from steam, and the pounding waters wore away mountains and made great canyons between the mountains, until 3/4 of the Earth's surface was water. Finally, the rains cleared, the clouds parted, and the sun shone through. It was a time for life to begin on Earth and in boundless seas.
We don't know exactly how our solar system was formed. After all, that was about 5 billion years ago. But we do know how unique we are. For life as we know it, our planet is not too hot and not too cold. And we possess what no other planet in our solar system possesses: liquid water.
Water filling the oceans and the seas, all interconnected in one boundless body of water, covering 75% of the Earth's surface. The oxygen we breathe, most of it, comes from the ocean that surrounds us. In 1969, we made our first successful visit to another planet when we put men on the moon. We knew there was no water there and no life. Our astronauts had to wear special spacesuits because of the temperatures and in order to breathe. When we landed instruments and TV cameras on Mars, there was practically no atmosphere or oxygen, no signs of life, and no water.
This is how important our ocean is to us. Without liquid water and an atmosphere, there'd be no oxygen to breathe, there'd be no green fields, there'd be no life as we know it on Earth. Everything on planet Earth is linked together. We know now that we must learn about our ocean, to care properly for its resources, and to make sure that we don't spoil it. To early man, this ocean was a thing of beauty, but also an insurmountable barrier, representing both on the sea and beneath it. Oceanographers, physicists, biologists, meteorologists, geologists, chemists, and more combine their love for the sea with their scientific curiosity.
This is the research submarine Alvin, which is jointly funded by the National Science Foundation, the National Oceanic and Atmospheric Administration, and the U.S. Navy. And I'm Dr. Robert Ballard of the Woods Hole Oceanographic Institution in Massachusetts. We are now preparing for a 2-mile dive to the Atlantic Ocean floor.
Man your launch stations. Man your launch stations.
These explorations have given us a new and interesting picture of the ocean floor as shown on this topographic map. Although we call it the floor, it is far from smooth. Actually, it's divided up into large basins by an immense underwater mountain range. We have explored the ocean floor along this mid-ocean ridge. This, though it is underwater, is the largest mountain range on Earth, higher than many mountains on land, longer than the Rockies, the Andes, and the Himalayas all put together. Unlike mountain ranges on land, these are split lengthwise, right down the middle. A giant crack or rift as much as 20 miles wide, 15,000 miles long, cutting into the Earth's upper layers.
The Alvin and crew are now ready to dive.
Lulu, Alvin, my hatch is shut, oxygen's on, blower's running, leaks and grounds are normal, surface ident lights and beacon are on. I'm ready to dive, permission to dive.
This is Lulu. Roger. Depth of water, 3500 meters. Permission granted to dive. Have a good one. Over.
Roger, diving.
This tiny craft and its crew are going down 12,000 feet into the mid-Atlantic ridge.
That more, that brecciated one we saw on the last dive.
Yeah, I think so too.
That's the outcrop we'd like to work on, huh?
Okay, I'm
You
here.
see it? Yeah, that's just right about there, right underneath that white sea anemone.
Yeah, I'm bringing the arm around. Okay, see the arm yet?
Yeah,
Okay.
it's just coming into view.
Okay. Let me have you in there.
Okay.
They're exploring this rift area for clues to the origins of the Earth. Here it is, the actual rift zone. Such rifts periodically release erupting lava. This is one of the most remarkable events ever observed. Fiery lava is pouring out of the side of the rift. A crack in the Earth's crust, far below the surface.
Such sights and sounds had never been seen or heard by Earth people. Although the volcano's roar is still heard on land in many parts of the Earth,
As it is on Iceland. Iceland is near the upper end of that great underwater mountain range, the Atlantic Ridge, where creation is still going on. So common here that people and animals accept this as a way of life. At night, even the sheep pause to watch curiously. We can see the top of one of those rifts or cracks in the Earth's crust that has pushed its way up through the surface, a process that has widened the area of Iceland. With every eruption, new rock is being added to the Earth's crust, new water to the atmosphere and the oceans. Off the coast of Iceland is a highly visible example of the power of this rift. In 1963, a ship captain, converging on what he thought was a burning freighter, found a new growing island, the result of lava leaking out and piling up in a shallow section of the rift. Eventually growing to over 50 square miles, this island was named Surtsey, after the Nordic god Surtur.
with all this lava coming up and all this shifting, there has to be motion, and there is. The accumulating lava causes growth all along the ridge, pushing the edges farther apart. A weaker edge gives way to a stronger growing edge. Extend around the entire globe.
At an overview, we see that the Earth is made up of a series of constantly moving surfaces called plates. whose motion is instigated by the rifts. Generally, these movements are slow, moving the American plate west about 2 inches a year. But occasionally, this movement along the rift still stick in our mind. Names of earthquakes and volcanoes: Pompeii, Krakatoa, San Francisco, Managua, and here in Guatemala.
But there are other movements in the sea that are not so violent. In fact, they're a benefit. The sea is a mighty circulating currents, and are pathways for the movement of sea life of all sorts.
Large bodies of water in the tropics catch and hold the sun's heat. These waters move toward the poles, bringing warmth to the colder latitudes, as you see by this map. One of the best known to us is the Gulf Stream. From the Gulf coast of the United States till it veers to the east and turns across the Atlantic, where it again hits land and divides, part of it going up the coast of Europe and part of it down the coast of Africa. The temperances of currents are extreme. Iceland, far up in the North Atlantic, is brushed by an arm of the Gulf Stream. Here we see a reasonably moderate climate, where farming and villages make up a viable community. At the same time, and in the same latitudes, actually even a bit more southerly, the tip of Greenland is a frozen mass of inhospitable ice fields. The reason? Greenland is untouched by any moderating currents. Currents are often called rivers of the sea, larger than any rivers on land. The Kuroshio, North Pacific, and California currents become the 9,000-mile-long North Equatorial Current, the longest west-flowing current in the world.
I'm Dr. Van Dorn of the Scripps Institution of Oceanography. When we watch a wave moving across the ocean, it appears that all the water in the wave moves with it. But actually, the water that composes the wave does not advance across the sea at all. As can be observed in a laboratory waveform, each water particle, rather than moving along in the direction of the wave, describes a circular or elliptical orbit with the passage of the waveform and returns to very nearly its original position. The wind blows against a flag and airways move across it, but the cloth doesn't move across the face of the flag. In much the same way does wind act upon water to create most waves. If the huge masses of water that comprise a wave actually moved, navigation would be impossible. A wave born of wind far out at sea grows to its full height on the energy of the wind. As the waves pass out of the storm area, their height diminishes, the distance between successive crests increases, and the sea becomes a swell. As the swell enters shallow water, it feels the drag of the ocean's bottom. Its speed slackens, and the wave height steepens. Then, with a spilling, tumbling rush of water falling into its trough, it dissolves in a seething confusion of foam.
The most damaging storm wave effects known to us are associated with hurricanes, because wind stress also piles water against the shores far above the normal water line. We fly over hurricanes, plot their courses using cameras and radar. Spawned at sea, hurricanes cause devastation on land as well as the oceans. In Andhra Pradesh, India, a storm tide driven by hurricane-force winds in November 1977 wiped out 10 cities and killed 20,000 people.
There are other waves, seismic sea waves called tsunamis, one of the most destructive forces of nature. The extreme shocks of underwater earthquakes cause swells, in a way similar to hitting this plastic tank of water.
In the deep ocean, far from land, they're barely visible, but they travel about 500 miles per hour.
Nearing the shore, in shallower water, the height of the tsunami builds. floods the coast, battering everything in its path, and then withdraws, taking with it houses and people, and carrying them all far out to sea. In 1946, people on the beaches of Hawaii were puzzled when the noise of the breakers stilled.
The waters receded, leaving a strange quiet. They were unaware that the behavior of the water was in response to an underwater earthquake that had occurred more than 2,000 miles away. Then the water came back, rising rapidly. The rise carried the ocean waters 25 feet above normal levels. The waves of the tsunami swept toward the shore with great turbulence. Francis P. Shepard of the Scripps Institution was there.
We were awakened about 6:30 by a tremendous roaring noise. We could hear the water rushing around the front of our house. Suspecting it was a tsunami, I ran to the back of the house. My wife was with me. We heard waves come up and smash in the plate glass in the front of the house, and saw the refrigerator go shooting past us on the left-hand side, and looking to the right, saw that my neighbor's house had been completely demolished by the water.
The tsunami did great damage. Houses were carried out to sea. People were swept away and drowned. It had taken the waves less than 5 hours to reach the Hawaiian chain, 2,200 miles from the quake, traveling at almost 500 miles per hour. Among the great forces that affect the sea are the tides. The amounts of water affected by tidal movements are enormous. Into Nova Scotia's Bay of Fundy alone, 100 billion tons of water are carried by the tidal motions twice each day. In the upper reaches of the bay, several miles from the ocean, even grasslands are covered for a short time twice a day by the high tides. And in San Felipe, Mexico, on the Sea of Cortez, a 30-foot tide periodically replaces fishermen's trucks with large fishing vessels working close to shore. Tides are the result of gravity's pull by both the sun and the moon on the Earth's ocean. Every drop of sea moves to the pull of gravity. Even though the sun is much larger, the moon has the greater pull because it's closer. Of course, at new moon, when the sun and the moon are in line, gravity's pull is greatest and brings the highest tides. The full moon and the tides combine to aid the life cycle of the Southern California Grunion, a small silvery fish the length of a man's hand. Not only has the Grunion come to know the daily rhythms of the tide, but it's adapted its spawning habits to the monthly tidal cycle, by which certain tides sweep higher on the beach than others. The Grunion takes advantage of the highest tide of the season to come onto the beach to spawn, to lay its eggs, and to fertilize them. Then they leap into the crest of the following wave and return to the sea, leaving behind a mass of eggs buried in the sand. Since the Grunion has chosen the exact time when the tide is highest, successive waves don't reach the eggs. They lie undisturbed until 2 weeks later, when the highest tides. These new high tides wash over the incubated and hatching eggs, and the newborn Grunion catch the waves that bear them out to sea. Oysters, mussels, and barnacles owe their very existence to the tides which sweep in, bringing the food which they're unable to go and search for. The ocean is the Earth's greatest storehouse of minerals. The whole land mass of Earth contained light and heavy minerals. Then, when the first rains came, they began wearing away the rocks and carrying more minerals into the sea. This runoff means mineral deposits in the shallower waters of the continental shelf. Here, dredges can bring up vast amounts of tin, phosphorus, iron, and titanium. Submarine volcanoes discharging through craters directly into the sea pour in boron, chlorine, sulfur, iodine, and all minerals, including silver and gold. When the ocean waters rise over the land, deposit their sediments, and at last withdraw, we are left with areas rich in salts and minerals, there for the harvesting. One of the greatest stockpiles of minerals in the world came from the evaporation of a great inland sea in the western United States. In the 1870s, teams of 20 mules each hauled borax from here across the desert to the railroads. Years later, the recovery of other substances began. Bromine, lithium, salts of potassium and sodium. This area now yields a major share of the potassium chloride found in the United States, plus a large share of all the borax and lithium salts produced in the world. Wherever great oil fields are found, they may be related to past or present seas. The great oil fields are reservoirs of oil trapped in the sedimentary rocks, laid down under the seas that invaded this part of the land some 200 to 600 million years ago.
In recent years, oil geologists have focused in a new direction, under the sea. Offshore wells are producing oil in California and Louisiana, all around the Gulf of Mexico, the Atlantic coast, and other offshore wells are bringing up oil from the Persian Gulf and in the North Sea, between Norway and England.
There's far more oil under the ocean than there is under land, but of course it's harder to get to it there and to get it out. An exploration crew from an American company discovered the field of rich oil reserves under the North Sea, between Norway and England. This is the North Sea, on a good day. It didn't get any smoother when the construction crew arrived. They must work their way down through 2 or more miles of ocean before they can even start drilling. But modern technology wins. In time, the drill rig becomes the pumping station over Discovery Well number 1. The North Sea project has become a veritable city at sea, including a 7-story hotel with recreation facilities for 1,000 workers. All of Europe benefits, as it supplies much of the needed energy to England and to the continent. From Emden, pipelines feed the Ruhr, Holland, Belgium, and France, bringing continued life support from the sea to this part of the world. The worldwide petroleum reserves at sea are great, but what of the power from the sea itself? The ocean contains a number of sizable potentials for power production.
Scientists and engineers are constantly at work to develop better methods to harness energy. Winds and waves, temperatures, currents, tides, the sea. It's never at rest. This is our heritage.
We are beginning to live in harmony with the oceans of Earth. We are finding more ways to utilize the resources of the seas. Our work now is only a beginning to help us to care for the enormous wealth held in trust for the world by the boundless